Okay. So, chapters, I don't even know why they separate chapters 22 and 23 in the book, but we do. So we got chapter 23 today, which is just more of an in-depth look at circuits. And so today we're just going to kind of get an introduction to it. Then we're going to have like two big labs over circuits, and we're going to use this PhET circuit builder lab, mainly because of the fact that actually trying to do that with actual like lab equipment. Charles?
Do you have an assignment out of the book tonight?
Yeah, but it's pretty short.
Okay.
Like this short?
Not that short. Probably about twice that length.
So about approximately 1 page long. I may as well type 2 pages.
Now, part of understanding circuits is when things are in series and when they are in parallel, and how that's handled mathematically. So on yonder purple sheet, so today the only thing we're really going to introduce is how resistors work in series versus how resistors work in parallel. And even if they're light bulbs, okay, light bulbs work because they have a certain amount of internal resistance. So you can have resistors, which sounds odd, or you can have light bulbs which act as resistors, but they produce light, okay? But mathematically, they're handled the same way. So here's the biggest difference mathematically, is that if you have resistors in series, like for example, like this diagram right here. So there's a couple of ways that you can tell if they're in series. One is simply to look and go, okay, hey, are they all in the same line? Physically, how you can tell if they're in series is that if I break that connection, everything's going to stop, okay? So if things are in series, if you break that circuit at any point, everything's going to stop. The other thing is being able to recognize the diagrams. So typically you're going to have batteries and you're going to have capacitors. How you can tell the difference is that batteries have like a long line and a short line. Capacitors have two lines of equal length, okay? That's how you can tell. It's like, hey, is that a battery, is that a capacitor? Capacitors have same length, batteries have different lengths. So let's say, for example, and this is the key part of the terminology, is that let's say you have two 10-ohm resistors. It's kind of a standard number to use on resistors, okay? They can be a lot bigger, but let's just say that they're 10 ohms. So part of the terminology when you're dealing with circuits is what they talk about an equivalent resistor. So here's how this plays out. If they said, okay, you're going to have two 10-ohm resistors in series. What is the equivalent resistance? So the idea of the equivalent resistance is that if you could take those two resistors and just replace it with one, what would the value of that 1 ohm resistor be if you took the place of those two? Okay? So it works mathematically. Because then you can use like V equals R, you convert it up, okay? You can do, you know, PIV, all that stuff. You're going to use those exact same equations, but a lot of times we don't want to calculate like individual segments, which you can. But a lot of times you want to get an idea of, okay, what's the overall circuit going to look like? If you replace those two 10-ohm resistors, and this is simple because they're in series, oh, that's like saying we're just going to replace the two 10-ohm resistors with one 20-ohm resistor. Because they're in series, all you have to do is add them together. Boom, you got 20. Parallel is a little bit sketchier mathematically, but you all can handle it thanks to the miracle of modern calculators. So if I have two 10-ohm resistors that are in parallel, okay, then I'm going to take 1 over 10 plus 1 over 10 and get 2 over 10, which is 1 over 5. Well, then I take the inverse of that, I get 5 ohms. So here's the difference. Is that if I have two 10 ohm resistors in parallel, that has the equivalent resistance of one 5 ohm resistor. But if I take those two same 10 ohm resistors and I stack them in series, that has the equivalence of one 20 ohm resistor. Okay? So even though the two resistors are the exact same, two in series has the equivalent of 120, two in parallel has the equivalent resistance of 5. Okay? So you would think, well, they should still be the same depending on how you hook them up. No, they're vastly different. So two 10 ohm in parallel is 5, two 10 ohm in series is like 20. Now the next question is, well, okay, well how does that work with the equations that we already know? That's a valid question. All right, so, oh, not what I wanted. That's what I wanted. No. Oh, I went through the hassle to build all these circuits, and now they're gone. Oh, okay, let me just. I hate technology at times. Hold on, let me real quick crank out a circuit. Bear with me. And yes, I like my circuits to be square angles.
What? It makes like simple cowardly circuits.
Ew.
Back off me. My circuit, my angles. You don't like it?
Makes it four-dimensional.
Ew.
I want the circuit to go to the past.
do not want
How messed up it is. Rotate on that z x-axis. So
You might as well have your own plug.
dimensional bowl, whatever ball, and there's like four
That's like the
dimensional
least
bowl.
robotic thing I've said all week.
With multiversal time travel.
You should print
Well,
some of the things I've
how
said
it kind
on
of
last
like
week.
if you look at if you roll a four-dimensional object in three-dimensional space, it's like the same as
I'll
like
tell you on like the way up.
if you like use a three-dimensional object and a three-dimensional sphere through a two-dimensional plane, how it like grows big and then like disappears and then like grow big. But like it does that in three dimensions and it's really weird. Because you like roll it
Okay.
and then it like
Make sure I got- I built
disappears
it
and
right
like reappears like over here and then like the pins get hit somehow and it's like over here at the same time.
Okay.
It's bad. It's not good.
So here's what I've got, and this is where the equations fit with the circuits. So I've got two 10 ohm resistors in parallel, okay? And here's how you can tell that they're in parallel, is that if I cut that line, notice that the circuit still is complete, it doesn't stop. It stops it flowing through this side of it, but I still have electricity flowing through the entire thing. So, let me reconnect that back up, okay? So, the beauty of this program, we're going to use this a lot because there's a number one, the math works out beautifully just like it's predicted. You can easily see if the circuit is complete. The light bulbs are brighter or dimmer than they should be, in terms of if that's how that compares to the math. There's no resistance within the wires, there's no resistance within the batteries. This is like a complete ideal world, okay? Everything just works like it should. As opposed to in reality, it's actually building circuits, which is always a train wreck, and that's why we use this. So, what I've got here is a 10-volt battery. Okay, so let's kind of put the form of this to use. I got a 10-volt battery, and I've got two 10-ohm resistors that are in parallel. So what I want to know is, what's the current at the top, what's the current at the bottom, and what's going to be the current at each branch.
What's the battery again?
10 volts. Math will work out fairly simple. what are you gonna start with? Vert it up, right? So, you've got a 10-volt battery. So, what's the equivalent resistance of the two 10-ohm resistors in parallel? 5. So that's like saying we're gonna have one 5-ohm resistor hooked up to a 10-volt battery. So what should be the current? 2 amps, right? I take 10 volts, I divide it by 5 ohms, I should get 2 amps, okay? So, miracle of modern math and computers, I do this, I get 2 amps, okay? So, in this situation, this is showing the movement of the electrons, okay? So, this is the actual reality of what's happening to the electrons. If you're old school, you can have it going as the conventional idea of the current going from the positive around to the negative, okay? Doesn't matter, notice that the amps just stay the same. So here's my question. If that's, do you want conventional or electrons?
Both.
Okay, well, we can't have both. It's one or the other, because then they're just going in opposite directions. Okay,
And it cancels out, nothing
and
happens.
nothing happened. Yay! No, okay. So, here's my question. If that's 2 amps up there, is it gonna be 2 amps down here? Or is it gonna be less?
2 amps. 2 amps.
Connor S., what'd you say?
2 amps.
Why?
Because it's still like, yeah.
It's still like, yeah, dear Lord, that's the most articulate explanation I've ever heard.
Am I wrong though?
Yes.
Yes, I don't know what it means.
It's Connor, it's automatically wrong.
You still.
I'm still waiting for a better explanation.
It's constant throughout the circuit.
Okay? Do I lose amps as it goes through the resistor? No, it's common misconception, okay? Conventional electrons doesn't make any difference. So if that's 2 amps up here, then that's gonna be, oddly enough, 2 amps down there. Okay? Cool, both 2 amps. Now, here's the next question. What's gonna be the current through each of the parallels then? Adding. Why? Okay? And since these are both 10 ohms, can the electrons tell the difference?
No.
No, they're both going to go, well, I have no advantage on either side. They're going to be the same. So I move this over here, and miracle of miracles,
Good luck, Charles.
go get them, Chuck.
Where's he going?
And that's 1 amp, and that's 1 amp, everything adds up to 2. Okay, that one's settled. Charles.
Yeah. See ya.
Okay. Now, let's talk voltage, okay? Voltage of all of them can be a little bit tricky. So the voltmeter has to be hooked up in parallel or series?
Series.
Parallel, okay? Because I'm measuring that voltage across those points, okay? So oddly enough, I have a 10-volt battery. Oddly enough, that's measuring 10 volts, okay? Shocking, wow, okay? Lauren's going, whoa, didn't see that one coming. Knocked me over with the feather. So here's the question. Now I'm going to measure the voltage across my resistors, okay? So here are your options. Those are 10 ohm resistors. That's a 10 volts. So each one could carry half, and each one would be 5 volts. Okay, so that's an option. So I've got 10 volts, the current gets split, the voltage gets split, each one's going to be carrying 5. It's an option. Other option is that they're both going to have the same voltage drop, and they're both gonna be 10, okay? So A is half, they're gonna be 5. B is the same, they're gonna be 10. C is that because of the fact that it's going through both of them, and they're gonna maintain, everything's gonna be the same, because it's half the current, I'm gonna double the voltage, and each one's gonna be 20.
See,
So A is 5, okay? B is 10, C is 20, okay? So how many vote A, that it's gonna be half the voltage?
okay, there's an end. No. Yeah, that's what I thought.
Nobody's on the A train, okay? What about the B train that's both gonna be 10? 1, 2, 3. Jaden, are you on the B train?
Abstain.
8. Okay. C train, gonna be 20.
I trust Thatcher.
Yeah.
4. Okay. So the C train is the left side of the room. So Thatcher, I think you've been nominated spokesperson.
Yep.
Why do you say it's gonna be 20?
Because the current is, oh no, I think it's gonna be 10 now.
Yeah, he's on Team B again.
Led us astray.
This is why I abstained. Also, B.
Come on, Thatcher, articulate why we're all gonna die
I
on
don't
this
know.
train.
Yeah.
Now,
Hey, say like, yeah.
oh my God.
If you like put it on the resistors, right, on each side of the resistor.
Yeah, I'm gonna put it on each side of the resistor, up, top and bottom.
I think it's 10 now.
Which is why you
mine.
Yeah.
Why are you back, why'd you change your mind?
Because for,
Because Ver,
Yeah.
what does Ver have to do with it?
because the
Very
current is
eloquent.
1 amp and the resistance is 10 ohms, so it's 10 volts.
Oh, so mathematically, if you Ver it up, each one has to be, because we just said that the current flowing through that is 1 amp,
I was right until.
and it's still a 10 ohm resistor,
Yes, one more.
so therefore the voltage has to be 10, okay? All right, so let's see what happens. Miracles, miracles. It's 10, cool, right? Now,
See, this is
what's gonna be the voltage drop across the whole thing if I measure the voltage from the top where it breaks down to the bottom? Is that also gonna be 10?
Like delta.
Cohen,
Why'd you ask me? Sure, why not?
any justification for it?
As the heart guides.
This is not Fry's AP Lit class where we're studying poetry.
I didn't even take that.
No,
Kevin,
I don't think it is.
you don't think it is? What do you think it is?
Because I think it'll still be 10. Because
That's what I said.
I was just asking why.
why?
Why
I
is it
think it's
still
still
10?
because if you're at your breaks, then you're going to be 2 amps, 2 current, and then you're going to be 5 because it's in parallel. So 2 times 5 is still 10 volts.
Okay? So mathematically, the equivalent resistance would be,
That's a reason.
that's a good reason. That's better than as the heart, what you put, as the heart guides.
Yeah.
God, that sounds
I
like,
like that.
okay, that sounds like a horrible, like Hallmark card. Okay?
Your intuition may be accurate.
So,
Why is it not accurate?
I got this. Whoa, that's bad. I got that. Who's the wrong one? And, hold on. Miracle of miracles, it's still 10 volts.
Good job, Kevin.
Okay? Yay for Kevin. Okay. So, here's the other reason that you look at your house being measured in, your house is wired in parallel, okay? You always assume that you have 120 volts. That's how electrical appliances are designed.
In America.
Well, if you start hooking things up in parallel and the voltage increases or decreases on the elements that you're gonna have running, that's gonna be a train wreck, okay? Gonna be an absolute train wreck. Now, we can change it up, okay? Instead of having 2 10s, I'm gonna make this one
Beefier.
15. Okay? So now I've got a 10 ohm resistor and a 15 ohm resistor in parallel. So let's start with this idea. What's the equivalent resistance of a 10 and a 15 ohm resistor in parallel?
6 ohms.
6, right? Because 1 over 10 plus over 15, take the inverse of that, you get 6. So what's happened to the resistance in the circuit? It's increased. Guys, went from 5 ohms to 6 ohms. Do I still have 10 volts?
Yes.
Still the same battery. So if I vert it up, I still have the 10 volts. So now I've increased my equivalent resistance to 6. So what should happen to my current? It should go down, right? Because now I have more resistance, I should have a smaller current. So somebody take 10 and divide that by 6.
1.67.
1.67.
7.
So I come up here,
What was that?
I have a current of 1.67. Cool, current's gone down. Like we predicted. So, what do those 2 currents still have to add up to?
1.67.
1.67. Now, here's the question. I got the 10 ohm resistor on the left, I got the 15 ohm resistor on the right. Which one's going to have more current, the left, the right, or is it still going to be split evenly between the 2?
It's gonna be the left side.
Why?
It has less resistance, so it's gonna have it.
Okay, so the electrons are going to decide when they reach this point, like, ooh, do I go right or left? I don't know. Oh, it's tough.
Left is easier. Go
Left is easier. Then why don't they all go that way?
Because they can't afford to do that. I don't know. Some of them are too poor. They can't afford to go left. So they have to go
Wait.
the hard way.
I'm gonna make an analogy. I can't do it anymore.
I'll make an analogy. Mays and Mays South. Yeah, the poor kids go to the harder school.
The 1.67. So
Yeah.
this is Mays.
Yeah, yeah.
Okay.
Mays South is the easy one.
Okay.
I wouldn't disagree with that, actually.
I don't get it. All right.
I want to make a neutral.
No.
Perfect analogy.
Now,
Stick the landing.
if we do this, how can we figure out, first off, let's just get a number. Let's see if we're right. So if I move this over here, I get that one being at exactly 1. And oddly enough, this one over here is 0.67. So they still add up to 1.67. You're right. This one over here has less resistance, so I have more current. That one on the right has more resistance, it has less current. Okay. Now, later on you'll see you can work this out as a proportion. So, what's the total resistance between the 10 and the 15?
6.
No. If I just add the 2 together, 10 and 15, I get 25. So, somebody take 10 and divide that by 25.
0.4.
0.4. Now, take 0.4 times 1.67.
Yeah, I already calculated.
What'd you get? If you take 0.4 times 1.67,
0.668.
so about 0.67, right? So this works out, and we'll spend more time going through the math and the intricacies of this. But the current that goes through these is proportional to the value of the resistance, okay? When you base it upon the total resistance, and we'll spend, we're studying Wednesday, we'll talk about that tomorrow in more detail. But if you can work it out as a ratio based upon the resistance, that you can work backwards and go, okay, hey, this is what has to happen. Now, so I've got more current, less current. Let's talk voltage. Is the voltage across each one of them still going to be 10?
Yes.
Why?
Because that's how voltage does its voltage thing. It doesn't change.
That's how voltage is?
Your resistor does not step down your voltage.
You can use verb.
Okay?
Yeah.
You could use verb,
Verb.
okay?
The math says.
So if I measure that voltage, I get 10. So if I measure this voltage over here, oddly enough, I still get 10. Cool. So if you ver it up, right? I've got a 15 ohm resistor multiplied, now somebody take 15 times 0.7. No. Yeah, 15 times 0.67. What do you get?
You'll get 10.
Yeah, you're gonna get your 10 volts, okay? So if you vert it up, if you take that current at 0.67 times that resistance of 15, you're gonna get this. Then over here, if you do the same thing, if I take that current of 1 amp, multiply that by my resistance of 10, I'm gonna get 10 volts. So here's what's gonna be important. In parallel, you still keep the same voltage drop across each one, even if they aren't the same. Got that? Good. Great. Now we're going to change it up.
Oh boy, it's like the resistances.
I'm going to clean this up just because I can't handle.
It's a reasonable assumption to assume that. Instead of 0.56.
Okay. Now, I've got two resistors that are in series. I changed them back to both being 10 ohms. Okay? They're both 10 ohm resistors. What's the equivalent resistance of two 10 ohm resistors in series? 20 ohms, right? So this is still a 10 volt battery, so what should the current be?
5.
So, miracle of miracles, I move this over here and I'm going to get 0.5. Is that still going to be 0.5 at any point in?
Yes.
It's not going to make any difference, okay? Don't believe me, we'll move this down here, we still get 0.5, okay? No matter where I am, still going to be the same. Let's talk voltage. So here's my question. Will the voltage, because that's a 10 volt battery, what's going to be the voltage drop across each resistor? Is each one still going to be, so here's choice A, same situation. Choice A, each one's going to be half, like I'm going to drop half the voltage across each one. So that's choice A, 5 and 5. Choice B is still going to be the same, each one is going to be 10, because I have the same current going through it and they're the same resistors. Or C, because I have two resistors in series, which says 20, then the voltage drop should also be 20. So I got A, 5, B, 10, C20. So how many are on the A train that across each one individually is going to be 5 volts? Okay? Each one across individually is going to be 10 volts. Okay? Each one across individually is going to be 20 volts. Okay. Vast majority of you voted B, that each one individually is still going to be 10 volts. Why?
Resistors don't drop voltage. They don't step down the voltage.
The
Okay.
current stays the same, right? It's the
Yeah,
same.
you're definitely wrong.
Stays the same.
That okay, the connotation,
Your vehicles are charged. If your current is the same, the voltage
What?
should change.
Stop that.
Yeah,
Hmm.
because.
Wow.
You
And
kept the current
like
the same.
0.5.
0.5 amp times 10 resistance would be 5.
What did you say, Jane Carroll?
it's the same. It's the same.
You didn't vote.
Well, I was the only one.
It's not the same phone.
Oh, I didn't see you there. I'm sorry.
And
So Jane Carroll, why did you vote 5 volts? Why were you the lone voice in the desert?
Because my EDD project does that when I do put 2 resistors. That is a voltage divider right there.
Okay. All right. So if you look at verb, right? If you look at verb, so the current going into this thing, whoa, that got weird. Whoa, that got weird. Let's see that. Okay? So I have a half an amp current going into a 10 ohm resistor. So if you ver it up, so if I ver it up, I have a half an amp multiplied by a 10 ohm resistor. Check my math, but 0.5 times 10 is
This many.
5.
I'm killing children in Africa.
So the next one, oddly enough, is also a, but what would be the voltage drop across both of them? That would be 10. So the voltage drop across both of them is 10, but individually it's going to be 5. Now, we're going to change it up. Now I'm going to take the top one, and I'm going to make that one a 15 ohm resistor. Okay? So what's going to happen to the current? Deacon. Good luck.
You mean the entire circuit?
Yep, in the entire circuit.
It's gonna drop.
Why?
Because the voltage is gonna stay the same through the entire circuit, and the resistance is gonna increase, so the voltage is gonna increase.
Okay. So, how can I find the theoretical value of the current? I know I've still got a 10 volt battery. What's the equivalent resistance of a 10 ohm and a 15 ohm? 25 ohm.
0.4.
So my theoretical current should be what?
0.4.
0.4. So I look at that, miracle of miracles, hey, the math works out, it's 0.4. So now, is that current still going to be the same at every point in there? Even though that's a 15 ohm resistor?
Yeah.
Yeah.
Still the same? You say. 0.4, 0.4. Current's the same all the way through, right? Cool, got that. Now let's talk voltage drop. So, is the voltage drop still going to be 5 and 5? Jacob?
No.
Oh, you said that with feeling.
I did.
Why?
Okay, because, wait, the voltage drops from where to where?
Across each individual resistor.
It's gonna be different because your resistance is different, because the 15 ohms.
Okay, what's the word that I hate?
Different.
You've used it 3 times.
Deceleration.
It'll be
Well, I didn't really know where it was going, But
Oh, use the word change, that makes a difference.
Deceleration.
Shut it.
biology, the resistance of one of the resistors increased, so that would mean that the voltage has to decrease
Okay?
because the current stays the same.
So if you VER it up, right? So is the current the same in both resistors?
Yes.
Still 0.4. Current's the same in both resistors, true? So if I VER it up, and this one is a 10 ohm resistor, and a current is 0.4, what should be the voltage drop across the bottom line? Should be 4 volts, okay? So I would think, oh, yeah, for math I got
This many.
4 volts. So that means the top one should have a voltage drop of what? 6.
Deceleration.
And oddly enough, the voltage drop across both of them is 10. Okay? So in series, your voltage drops have to add up to what the entire voltage is across the battery, if it's a simple one like this. Okay, got that one. All right. Now,
Must be like resistor, parallel resistor.
okay. So here's what I've got with this one.
What the?
Magic.
It's magic. So I've got a 9-volt battery. I've got a light bulb with 10 ohms.
I don't think that second light bulb's doing anything.
It's not.
Oh,
When the
really?
switch is undone, it's.
I've got a switch in here. Okay? I've got a switch in there. So here's what I want to look at. So I've got a switch. Are the bulbs in series or are the bulbs in parallel?
Parallel.
Bulbs are in parallel. Okay? And I've got, basically, with that switch being closed, I've got that light going like this. So here's what's going to happen. I'm going to open up the switch. Okay? I'm going to open up the switch. So, first off, if I open up the switch, will any electricity flow out to the other one? So if I open up that switch, which is right here in the middle, okay? If I open up that switch in the middle, will the other bulb light up?
Yes.
Why?
Because the electricity doesn't have anywhere else to go.
Has to go the other way.
That's the only way to complete the circuit.
Yeah, it's the only way to complete the circuit. So right now, if I look at the current, that current's at 0.9 amps, and the voltage across the bulb is, let me switch those up, 9 volts. Does that make sense? I only have one bulb, right? Okay? One battery, whatever, so that voltage drop, if you only have one thing, whatever the voltage is of the battery, that's gonna be the voltage drop across the resistor, the bulb, whatever that is, because it's the only place for it. Okay? So, let's talk about what's gonna happen when I open up that switch. What's gonna happen, number one, to the current? Is the current gonna increase, decrease, or stay the same? Decrease. Why?
Yeah.
Why will the resistance increase?
More resistance.
You have 2 bulbs in series, so because now all of that electricity is just gonna be flowing out around like that, right? Okay? So you're saying the current is going to decrease. What's gonna happen to the voltage across the bulb? Increase, decrease, or stay the same? Jacob,
Decrease,
why?
because the voltage now has to be shared between the two bulbs, like within one bulb and within the other bulb, but the drop between the bulbs will stay the same.
Okay? So, if I open up the switch,
Yes.
We just did that, it's the same as.
It's same as the two resistors.
yeah, it's just, it was
Because
what we just talked about, right? Okay? So, now, that's 4.5, but if I measure the voltage drop across the whole thing, screw that up, the voltage drop across both of them is going to be, no. When I closed, let me close that back up. When I open that, what's going to happen to the total resistance in the system? It'll increase because you have two bulbs that are in series. Okay, two bulbs are in series. So my total resistance will go up. So as my resistance goes up with the same voltage, my current has to go down. Okay. Now I'm going to change this up a little bit. So I'm going to trash that. I'm just going to complete that.
Whoa.
Come on. Actually, I don't like that.
Right now?
The battery's
Yeah.
on fire.
Current animation speed reduced to less than
I like that
1%
I know.
normal.
Well, it's funny, they, in the name of political correctness, they don't have this anymore. This is a true story. You see, you can have like different things in the circuit, like a coin, an eraser, a paper clip. They used to, and they took this out probably 5-6 years ago. They used to have a German Shepherd that you could put in. No, that's honest to God true story. Okay, like you can measure the resistance across a German Shepherd.
No.
So, they don't have that anymore, but that's a true story. The old version, the old program, they used to have a German Shepherd.
Did
Okay,
it catch fire like the battery if you put too much through it?
no, but it,
Why is the current still there?
it was interesting, let's put it that
Why
way.
is your battery like
I don't know what happened.
Because the current is 89,000 amps.
Yeah,
Oh, I guess it's because it's not connected.
There's 89,000 amps
I
of
think it's the
current.
light bulb on the right side.
It's like not actually connected
not
to
connected
the.
correctly.
oh, there we go. It's like, this should work, okay.
Hey.
Oh, something's happened. Oh.
Yeah, delete that. And then
I much prefer my
Battery's not on fire
89,000
anymore.
amps
That's what
of
we're
current.
That's like.
There we go.
There we go. Okay. So, now we're not flaming the battery. We're concerned each other. So, I got a current of 0.9 amps. The voltage is 9, is up here, that's going to be, I got a 9-volt battery, and I've got a current of 0.9 amps, so therefore the value of the resistance inside the bulb is 10 ohms. Okay? Now, here's what I'm going to do. First off, when I close that switch, are the bulbs going to be in series or are the bulbs going to be in parallel? Parallel. So when I close that switch, what's going to happen to the current in the system? Increase, decrease, or stay the same?
Before the swing increase.
Increase.
When I close that switch in the middle, what's gonna happen to the current? Increase, decrease, or stay the same?
Increase.
Increase, why, Kevin?
Because the resistance goes down when it's in parallel because you inverse it.
Okay, so having two 10-ohm bulbs in parallel would be the equivalent of having one 5-ohm. Okay, so two bulbs in parallel is the equivalent of having less resistance. So therefore, the current should go up. So miracle of miracles, the current at that point still stays at 0.9. That didn't change. But over here, when I close it, that's going to go up to 1.8. So the individual ones stayed at 0.9, but the overall current went up to 1.8 because it has to be split. Okay? Now, so this is why if you ever become homeowners and breakers in your house are rated at like 10 amps, 15 amps, something like that.
Sounds a lot.
So what happens is that you tend to throw breakers when you have too many things in the house being run at the same time. Okay? Like you have like a blow dryer and a coffee pot and an iron, and if they're all on the same circuit, and as you run those more and more and more, you're drawing more and more things in parallel. So what's going to happen to the current?
It's gonna rise.
It's going to go up because of the fact that you have the same voltage, you have decreased the equivalent resistance, the current goes up. If you have a 15 amp breaker, if you exceed that, guess what?
The breaker
The
trips.
breaker throws, and then you've got to go back down and reset it. That,
I want.
Is the voltage drop across each light bulb the same in series as in parallel?
let's see. So, that's a 9-volt drop across the battery. So what should be the voltage drop across each bulb? Is still going to have 9 volts. So in that situation, they're both going to still be 9 volts. However, let's make